So in this 55th lecture, I'll discuss one last problem based on a center tap full wave rectifier, and look at the statement of the problem. This is a problem here. An AC supply of 220 volt 50 hertz is applied to the primary of a 10:1 center tap transformer used in a full wave rectifier. So let's draw the circuit based on the data that is given to me here. So it says a 220 volt 50 hertz supply. So transformer is here and a center tap transformer is there. So I draw the circuit diagram of a center tap transformer first. Center tap full wave rectifier. So this is the circuit diagram for this. You have a center tap transformer here initially. Say this is your center tap transformer. It has been tapped at the center. Suppose here it is tapped at the center. And of course, when it is a center tap full wave rectifier, it uses two diodes, and these are the two diodes. And of course, from the center tapping only I take out the load from here, RL. Initially I have drawn this. So whatever data is given to me, that I'll apply here. This is my center tap transformer. Now look at the problem. Look at the statement. An AC supply of 220 volt 50 hertz is applied here. Means the signal which is applied here is a AC signal of 220 volt 50 hertz. Means what is applied here is 220 volt and 50 hertz is the supply voltage from here to the primary of 10:1. So this ratio is 10:1. Means if 1000 turns are here, it will have 100 turns. So it will be 10:1. Apply to the primary of a center tap transformer used in a full wave rectifier. If the diode used has a forward resistance of 100 ohm, means every diode, this diode is having a forward resistance of 100 ohm. This RF is given to you 100 ohm. RF. Similarly for this also, the forward resistance of this is also, I name this as RF, and the load resistance, that is RL, is 1100 ohm. This is 1100 ohm. This is given to you. I name this as RL. Now suppose I say that this voltage, I name this voltage as Vs. This is the supply voltage, and say this is point A and this is point B, and the input, I say that this is the input Vi. Before I come to the problem, I am interested in this Vi. What is this Vi? What I am interested in, this Vi. Of course, either between these 2 points or between these 2 points, the voltage is Vi. Now from here I can say this 220 volt RMS, this is Vs which is being supplied from here. So this will be stepped down here, and suppose I say I apply the transformer turns ratio formula here, that is V1 upon V2 is equal to N1 upon N2. So I can say that Vs upon VAB, between this and this point, Vs upon VAB. This is the point to be remembered here. Complete secondary is this. So Vs upon VAB is equal to V1 upon V2 is equal to N1 upon N2, that is 10 upon 1. So I can say that the value of VAB, that is the voltage between the points A and B, VAB will be Vs upon 10. VAB will be equal to Vs upon 10, that is 1/10 of this, and the value of Vs is given to you, that is 220 volt here. What is applied is 220 volt. So I can say that value of VAB will be 220 upon this much, it is 22 volt. Of course it is the RMS value. Until and unless it is not mentioned that it is a peak value or peak to peak value, always take it as a RMS value. Now what is Vi? So this Vi is equal to, it will be half of this, that is VAB upon 2. This implies that this VI is equal to 22 upon 2. This VI is 11 volt RMS. That is very important to understand here. 11 volt RMS means this VI which is applied here, which I obtain here after applying this center tap transformer, it will be 11 volt RMS value. So if I plot this VI, just see, if I simply plot this VI here, I am interested in plotting this VI. Suppose I plot this VI, it will be like this. This is VI with respect to omega t. If I plot this VI, let me use another color. This VI is something like this. It is a sinusoidal voltage. I am not drawing this Vs, which has been, this is nothing. VI is the step down version of this Vs after being passed through this step down center tap transformer. So this is VI, and this VI is having the RMS value 11 volt. It is 11 volt RMS. 11 volt RMS value. So if I say that what is the value of Vm from here, this implies that this Vm, if I say that this value is Vm, it will be equal to 11 root 2. 11 root 2, or I can say that the signal which is applied here is a signal of maximum value 11 root 2, and of course the frequency is 50 Hertz only. So very first point is to understand this only. Next is, let's draw this again. I am interested in the output current, for example. I draw the output current also, although it is not asked in the problem, but just to explain you. Again, this is omega t here, and I drop down these points from here. I simply drop down these points here only, and of course working we have done, the points are 0, this is pi, this is 2 pi, 3 pi, 4 pi, and so on. And the output which I'll obtain here, suppose I say this is the output current IL across this load, it will be of course a full wave rectified of this nature. And the value of this I, instantaneous value of this, I can say, if this is I can say the value of this is Im sine omega t. Frequency will remain same, where Im is the maximum value of this. This is Im that we have done many times, and this Im is nothing, it is equal to Vm, it is equal to Vm upon Rf plus RL, where Rf is 100 ohm and RL is 1100 ohm. This Im is equal to Vm upon Rf plus RL. So this is the input and output waveforms that I have drawn here, what was given here with respect to that only. Now let's come to the problem again. Determine the peak RMS and average value of the output current. It says find the peak value of this. First point is to find the peak value. So I am solving the first part. When it says that find the peak value of this, what will be the peak value of this? That is, peak value means Im. First part, you are interested in the value of Im. Now this Im is equal to Vm upon Rf plus RL. Vm upon Rf plus RL. And the value of Rf, value of Vm. I am not solving the complete, I will not give the full answer, but Vm we already know that this Vm is 11 root 2. So I can say it is equal to 11 root 2 upon Rf. What is Rf here? Is 100 plus 1100. 100 plus 1100. This much ampere. Peak. then the average value of this, the average value means IDC. This IDC here. I am interested in this IDC, and we have derived that the DC value of this IDC is equal to twice Im by pi. That is, again it will be 2 times, so 12 into root 2 upon this much. You substitute the value of Im. You substitute the value of Im is equal to this much here. So it is 2 into 11 root 2 upon 100 plus 1100. You can find it very easily from here. Next point says find the value of the RMS value, and you know that IRMS of this, RMS value of this for a full wave rectifier is equal to Im upon root 2, and simply you can find out the RMS value of this. Next is, it says determine, first part is done. Second part, DC output power. Look at the second part, the solution of the second part. It says that find the DC output power. Now how to find the DC output power? That is, we are interested in PDC. PDC is IDC square into RL. IDC you have already calculated from here. This is your IDC. Substitute this value here, and the value of RL is 1100. If you substitute this value, you will get the final answer for this PDC. So I request you to do the calculations on your own, please. Next part is the peak inverse voltage. What is asked in the next part is the peak inverse voltage. I'll just turn it. Is the peak inverse voltage, PIV. If you remember, I told you that the peak inverse voltage for a half wave rectifier, peak inverse voltage for a half wave rectifier, we have derived that this is equal to Vm. Vm means, just hold on, Vm means the maximum voltage which is applied at the, which you obtain from the secondary of the transformer. And peak inverse voltage, just a quick revision, of a bridge rectifier, sorry, BRIDG, of a bridge rectifier is, again it was Vm, but on the other hand the peak inverse voltage of a center tap full wave rectifier, CTFWR, which stands for center tap full wave rectifier, I write it like this, it is equal to twice of Vm. It is equal to twice of Vm. So Vm is this. We have seen that the value of Vm is 11 root 2. So it is 22 root 2 again. It is 2 Vm. So it is, I can say it is equal to 2 into 11 root 2. So it is finally 22 root 2. I hope that this is clear to you. Next part. Percentage regulation. Now percentage regulation, as far as the percentage regulation is concerned, I told you that, next part, I am solving it here. The percentage regulation means voltage regulation. Percentage regulation. In general, the voltage regulation, I told you, it is equal to VDC at no load minus VDC at full load upon VDC at full load. DC voltage at full load. This is what we have read, as well as I told you the shortcut also, that is equal to small rf upon RL. So from here you can find the value of voltage regulation. Of course, you want in percentage, you can multiply this by 100 and it will be percentage. As simple as it is. Next part is to find the frequency of output signal. Next part is to find the frequency of output signal. Suppose I say that the frequency of output signal is FO. Frequency of the output signal. Suppose I say it is equal to FO. Now look at this. the frequency of this signal, if you see that the frequency of this signal is 50 hertz, the frequency of this particular signal is 50 hertz. Now this signal or this particular function is now rectified and you get this type of signal here. Now if you look at the time period of this, the time period is 2 pi, means this wave is repeating after 2 pi. On the other hand, here it is repeating after pi only, 0 pi, 2 pi, 3 pi, means the time period is halved. If the time period is halved, automatically the frequency is doubled. So I can say that the output frequency is twice the input frequency. So the input frequency is given to you, it is 50 hertz. Of course, if this is 50 hertz, after being stepped down also, it is the amplitude which is being stepped down. The frequency remains the same. So here also at the input, this is also 50 hertz signal. So the frequency of this output signal will be 100 hertz. So for the time being, I stop it this rectifiers here. The next topic that I start with is filters. Now let me just simply define first of all what do you mean by filter. When we define filter, I say that simply in very simple language, I say that it is nothing, it is a frequency selective electrical circuit. This is how I simply define a filter. Now I'll just explain what it is. What do you mean by filter and why we need this filter? Now if you remember, we started with we are mainly dealing with a regulated power supply. This is a regulated power supply that I started with. Regulated power supply. I started this unit with this topic, regulated power supply, and we say that initially we have a transformer here, followed by a rectifier, then you have a filter, then you have a regulator, and finally it is given to a load here RL. This is which I have done with you. Now rectifier I have discussed with you. This is a rectifier. Now what happens that this rectifier, if you see, this is a rectifier. This what we have done. This rectifier, we apply some AC signal here, and we have seen that the output that we obtain is a pulsating DC. But at the load, I am not interested in this kind of DC, but I am interested in this kind of DC. This is a pulsating DC, and we have seen that one more term we obtained is a ripple factor. That is, this pulsating DC or the output of this rectifier has some AC component here, and by what amount these AC components are present, by what amount these AC ripples are coming, by what factor these ripples are present, that is called the ripple factor. And even we have seen that this gamma ripple factor for a half wave rectifier, it is equal to 1.21, and this gamma even for a full wave rectifier, when we are saying that it is better, there also you have the maximum ripple factor is 0.48. Still 48% ripples are present in case of full wave rectifier also, and these ripples has to be removed. Now these ripples are nothing, these ripples are the high frequency components. These are the high frequency components in this rectified output, and we are interested in a DC. Remember that the frequency of a DC signal is 0. So it is a low pass filter. We need a low pass filter in order to find this. So in order to improve the ripple factor, before this load RL, I apply an electrical circuit here. I apply a electrical circuit which will pass. It has low frequency as well as high frequency component, which will pass the low frequencies and stop the high frequencies. Such particular electrical circuit in general is called a filter, and we say it is a frequency selective electrical circuit, and our focus here is on low pass filter. Although there are various type of filters, you have high pass filters, band pass filters, band stop filters, band reject filters, but for a regulated power supply, our focus is on low pass filter because we are interested in a DC supply where the time period should be maximum, and of course DC. Ideally this frequency should be 0. For this purpose, the kind of electrical circuit we apply is a filter, which is a frequency selective electrical circuit. I'll continue with this in the next lecture, and maybe there's a possibility that I'll give a small, we'll add some videos from next lecture in parts. So thanks for the time being.